This short video is a reminder of a few things with ionic bonds. So we're going to talk about ionic bonds and what they are and how they work and how to write them. So remember that in ionic bonds, one element gives up electrons and the other element gains electrons, and the ions are now attracted to each other due to these opposite charges. So let's consider two elements. I'm going to start with the Bohr model, and the two I'm going to pick are two very simple ones. I'm going to pick lithium, and I'm going to pick fluorine. Remember that lithium has 3 protons in its nucleus. It's going to have 1, 2, 3 electrons, and therefore 1 valence electron. Fluorine, on the other hand, has 9 protons in its nucleus. It's going to have, therefore, 9 electrons. And because it has 9, it has 7 valence electrons. So what's going to happen is lithium is going to give up this electron. And when it gives up the electron, it forms a +1 ion. Fluorine is going to gain the electron. It's going to form a -1 ion. And then they're attracted to each other. The easier way to draw this is to just use the valence electrons through what's called a Lewis structure. So if I were to draw lithium, it'd be lithium with 1 dot. And then if I were to draw fluorine, we'll do fluorine in blue to make it easier. Fluorine, there are fluorine 7 dots. And this arrow, red, is going to show lithium giving up the electron and giving it to fluorine. And what ends up happening is you have lithium with a +1 charge in a bracket, and it's attracted to fluorine. Fluorine's got 1, 2, 3, 4, 5, 6, 7, 8 electrons now, and therefore the -1 charge, and they're attracted to each other. In a more complicated example, let's say we have lithium, which once again has 1 valence electron. This time it wants to combine with oxygen. Oxygen has 6 valence electrons. Of course, lithium is going to give up its 1 electron to oxygen, and it's going to form the lithium plus ion. Oxygen now has got 1, 2, 3, 4, 5, 6, 7 valence electrons. There's the one from lithium. It's got a minus charge. The problem is oxygen is still unhappy. So we'll draw a little frowny face on oxygen right there. He's unhappy. In order to be happy, he has to follow the octet rule and be full. So we need another lithium atom. We'll do this one over here. This lithium is going to give up its valence electron to oxygen. And when we're all said and done, what we end up happening is if lithium with a +1 charge, we have our oxygen right here. He's got his original 6 plus the 2 he got from lithium, so he ends up with a -2 charge. And then the other lithium with a +1 charge. And together, this compound would have the formula Li2O in order to ensure that every single atom or element in the compound follows the octet rule. Which brings us to our next topic, which is writing the formulas for ionic compounds. In order to know the formulas for ionic compounds, you have to know the charge that a common atom is going to form on the periodic table. So for example, you know that anything that's an alkali metal in group 1 is going to form a +1, or a halogen in group 7 is going to form a -1 based on where they are. You also should know those 6 polyatomic ions that I expect you to know from last time. So let's look at a couple examples. We're going to start easy and get more difficult as we go on. The first one is potassium iodide. So we go to the periodic table, we find potassium. Potassium is an alkali metal, so it is the letter K for its symbol, and because it's an alkali metal, it's going to form ions with a +1 charge. Iodine is a halogen. It is iodide ends in ide. It comes from the periodic table, so it's iodine. It is a halogen. So the symbol is I, and because it's in group 7, it has 7 valence electrons, and it's going to form a -1 charge. Remember, our rule is that all ionic compounds have to be electrically neutral, so if this does not equal 0, which it does, you're going to crisscross the charges, but since this equals 0, the very simple formula for potassium iodide is Ki. You could also crisscross and put a 1 there, but we never write a 1 in chemistry, so that'd be bad. So let's do the next one. It's aluminum oxide. The first word is aluminum, so we find aluminum. It's an element on the periodic table. Aluminum is in the 3rd column, not the transition metals, so it's going to form a +3 ion. Oxide ends in ide, so it comes from the periodic table. It's oxygen. Remember that oxygen is a -2. These are not equal to 0, so this is not 0. So what we're going to do is we're going to crisscross and swap the charges, and what we're left with is the compound Al2O3. And if you think about what this means, I'm going to write this in gold so you can see it. It means that I have two ALs, each one with a +3 charge for a total of +6. And I have 3 O's, each with a -2 charge for a -6, and -6 and +6 together equals 0. So the compound is electrically neutral. Let's try the next one. We have calcium hydroxide. We see calcium, it comes from the periodic table. It's not a transition metal, so it's Ca. It's an alkaline earth metal. It's got a +2 charge. Hydroxide ends in I, but it's that weird, rare polyatomic ion that ends in "ide." You gotta remember that it's OH with a minus charge. And so what we're gonna do in this case is, because this does have -1, just so we're sure, this does not equal 0, so we're gonna have to crisscross the charges. The 2 is gonna go on the OH, the 1 is gonna go on the Ca. And we're left with CaOH2. However, if I put the 2 just here, the 2 applies only to the hydrogen. So in order to indicate the 2 is on the entire hydroxide, we're going to put the hydroxide in parentheses, and that's our final formula, CaOH2. Finally, the last one is iron 2 chloride. This 2 should be the dead giveaway. Iron is a transition metal. We find it, it's Fe, and because we have that 2, we know the charge is a +2. Then we go find chloride. Chloride ends in I, so it's a chlorine. Chlorine's a halogen, so it's -1. Once again, these both don't equal 0, so we'll crisscross our charges. 2 down there, 1 down there. Remember, we don't write a 1, so we're left with FeCl2. And that's really how you write the formulas for ionic compounds. There's 1 or 2 that are trickier, but they're not super tricky. So this brings us to the last little topic of review, which is how to name ionic compounds. So let's do a few examples. So we'll start with an easy one. This is when both elements come from the periodic table. The first word is the name of the first element. In this case, it's magnesium. The second word is the name of the second element with the ending changed to "ide." So this element is bromine, and so this compound is magnesium bromide. The second example is a little more complicated because this first one is a polyatomic ion, but it's still the same. If the first word is a polyatomic ion, the first word is just the name of the ion, so in this case it's ammonium. The second one is still the I, it's the element from the periodic table, so it's iodine. We change the name to .ide, so it's ammonium iodide. The third one has that in reverse, so the first word is the name of the first element. This is sodium. The second word is just the name of the polyatomic ion. It doesn't come from the table, so we don't have to change its ending. PO4 is one you should have memorized. It's a sodium phosphate. And then finally, the last one is the most tricky because you have this first word, it's a metal from the periodic table. It's manganese, so Mn is not magnesium, it's manganese, you get these confused. But manganese is a transition metal, so we have to figure out its charge. So we're going to leave a little space in parentheses for the charge. The last word is the polyatomic ion, that is carbonate, so this is manganese something carbonate. And then we got to figure out charges. And remember that ionic compounds are electrically neutral. We know carbonate is -2, and there's 5 of them, so together that's -10. So for this to be neutral, I've got to get +10, and since I have 2 manganese, each one has to give me 5. So this is actually manganese 5 carbonate. And that's it for naming ionic compounds. Remember, though, that if you have a transition metal as your metal, you have to put the charge in parentheses, and that's the only hard thing with doing this. So hopefully this review helped, and good luck.